When you hold a thought in your mind, a phone number, a face, an idea, how does your brain actually do that? For a long time, we've had a pretty standard answer. But what if that answer is missing a massive piece of the puzzle? Okay, let's get into this, because a brand new paper from David Clark and L.F. Abbott throws a huge curveball, suggesting a wild new way our brains might make memories. Not by slowly carving them in stone, but by instantly freezing them right out of chaos.
So the classic way we picture the brain is like this incredibly complex but pretty stable electrical grid. You've got the neurons, and they're firing away like crazy. And the connections between them, the synapses, yeah, they change, but the assumption has always been that they change slowly, over hours or days or even longer. That's what we call learning.
But this new theory comes along and asks a really disruptive question. What if that wiring, that synaptic blueprint, isn't stable at all? What if it's just as jumpy and dynamic as the neurons themselves, constantly rewriting itself second by second? And if that's true, it would fundamentally change everything we think we know about how the brain computes.
To really wrap your head around how big of a deal this is, we first got to go back to that bedrock idea of modern neuroscience, the fixed blueprint. This is the world where fast neurons do their thing on a solid, slow-to-change stage. And the main tool for change in that classic model is something called synaptic plasticity. It's a really simple but powerful idea. You've probably heard the phrase, neurons that fire together, wire together. That's it. When two neurons are active at the same time, the connection between them gets stronger. And this is how we've always believed stable, long-term memories get etched into our brain's circuitry.
All right, so how does this new model just flip the script? Well, it takes that idea and turns it completely on its head. It says, let's treat both the neurons and the synapses as fast, dynamic things that are constantly interacting. They're not a performer and a stage anymore. They're more like two partners in a very, very fast dance. This slide here really nails the difference. So in the classic view, you've got these dancers, the neurons, performing on a solid dance floor, the synapses. The floor shapes their performance for sure, but they're not changing the floor itself in real time. But in this new model, the dance floor is alive. It's shifting, rising, and falling with every single move the dancers make. And that, in turn, changes how the dancers move. It's this non-stop, high-speed feedback loop between the two.
So, if this is true, what kind of things could a brain like this actually do? What new tricks does it have up its sleeve? Well, the researchers basically created a map to explore all the wild possibilities that pop up when you let that blueprint change from moment to moment.
And this map you're looking at is called a phase diagram. Now, it might look a little complicated, but just think of it like a control panel for a simulated brain. It's got two main dials we can play with. The G dial controls the strength of the underlying, stable connections. You can think of that as the brain's basic wiring. And the K dial, that one controls the strength of those fast-changing connections, that plasticity we're talking about. By just turning these two dials, we can explore a whole zoo of different brain states.
Let's start on familiar ground. When we turn that plasticity dial, clunk, up into positive territory, we get what's called Hebbian plasticity. And that is our old friend, the fire together, wire together rule. It acts like a magnet, an attractive force that creates a positive feedback loop, making active pathways even stronger.
But here's the first big surprise. When you add this fast Hebbian plasticity to a chaotic network, you'd think it would make things more active, right? Nope, it actually slows it down. You can see it right there in region 2 on the diagram. The chaotic firing gets less chaotic. Those strengthening connections create a kind of synaptic drag that pulls the whole network's activity into a slower, more structured state.
So, what happens if we twist that K dial the other way, into the negative? Then we get something called anti-Hebbian plasticity. It's the exact opposite idea. Fire together, wire apart. It's a repulsive force that actively makes connections weaker when neurons fire together, essentially pushing their activity away from each other.
And the effect, as you can see in region 3, is the polar opposite of that Hebbian drag. This repulsive force actually speeds the network up, and it introduces this really distinct rhythm and oscillation. The whole network starts to pulse with a faster, more coordinated beat.
Okay, so far this is super fascinating, right? But it's still a world where the neurons are pretty much the stars of the show. But when the researchers really started to crank up the strength of that Hebbian plasticity, they stumbled onto something that completely flips our entire understanding of what's driving the show in the first place.
This phenomenon is called timescale segregation. It's a bit of a mouthful, but the idea is actually pretty straightforward. It just means that under these conditions, the system splits into two different modes of operating, one that's really fast and another that's really slow.
This slide here is basically the proof. Think of it as a map of all the different speeds happening inside the network. And you can clearly see it's split into two bands. You've got a fast band, which is still being driven by the neurons, but, and this is the crucial part, a new slow band emerges. And this slow band, it's driven by the synapses. And here's the kicker. It's this slow, synapse-driven band that is now in control. It's steering the entire network.
This leads to this incredible quote from the paper, which just perfectly sums up this upside-down way of thinking. It suggests we should look at the network not as neurons connected by synapses, but as synapses connected by neurons. The dance floor is now leading the dancers. It's a total paradigm shift. So this mind-bending, synapse-driven state is where the most stunning discovery of the whole paper comes to light. It's a totally new and incredibly powerful mechanism for working memory, and they call it freezable chaos. And the process itself is just beautifully simple. First, the network is just humming along in its dynamic, chaotic state. You could call this the brain actively thinking. Then, for step 2, you just stop the synaptic plasticity. You literally freeze the dance floor in place. And instantly, all that chaotic activity collapses into a stable pattern. It becomes a memory of the exact state the brain was just in. And to erase it and start thinking again, you just unfreeze plasticity and boom, the network seamlessly goes right back to its chaotic state. And this graph shows it happening right in the simulation. You see the wild, chaotic activity on the left. Then, at that first dotted line, plasticity is switched off. The activity immediately settles into a stable state. The researchers even test it. They poke and prod the neurons, but they just relax right back to that stored pattern. It's a rock-solid memory. Then, when they turn plasticity back on, the chaos just resumes as if nothing ever happened. So, what does this discovery of freezable chaos really mean for us? Let's unpack the implications, because they are profound, not just for how we understand our own minds, but for how we might build the next generation of intelligent machines. Well, first, it's a completely new tool for our working memory, the brain's mental scratch pad. And unlike a lot of other models, it can store any new pattern instantly, without needing any prior training. But the most radical idea is how it does it. Memories aren't formed by turning plasticity on. They're formed by turning it off. And that also means wiping a memory is effortless. You just let the system go back to being dynamic. This could be a huge inspiration for building more efficient AI, especially for things like in-context learning, where a model has to quickly absorb new info without being completely retrained from scratch. This research really forces us to just reconsider the very nature of what's stable and what's changing inside our heads. It suggests that what feels like a stable thought might just be a brief, frozen moment in a relentless, chaotic dance between our neurons and synapses. And it leaves us with this really tantalizing question. If our brain can literally freeze chaos to create a memory, what other incredible secrets are still hiding in its complex dynamics?